We're going to introduce the transport equation, which is perhaps the most important equation in dynamics. And the reason why this is so important is that because when we apply the laws of mechanics, so Newton's laws, we have to observe the kinematics. Remember, we have to observe the acceleration within an inertial reference frame. However, in reality, we make most of our observations in real life from reference frames that are not inertial. So we'll oftentimes make observations of how a point moves on a rigid body because that's the instrumentation that we have. And so if we observe the kinematics of the way a point or a particle or another rigid body moves from a non-inertial reference frame that's perhaps rotating or it's accelerating in some way, and we want to apply Newton's laws or Euler's laws, which we'll get to, we have to do that in the inertial reference frame. Now, I should note, we'll see by the end that this is reference frame independent. So as long as we've got two different reference frames, they can be called whatever we want. It doesn't have to be an inertial reference frame per se. We can transport our observations of the time derivatives between them using this equation. Now so far, to find the time derivative of point P as observed in this inertial reference frame, which is the velocity of P with respect to O, what we've done is we've taken the time derivative of these individual position vectors, the position vector of O prime with respect to O, and the inertial time derivative of the position vector of P with respect to O prime. And this gives us an expression in which we have what we call the translational component, which is the velocity of O prime, a point on the body with respect to O, and then the inertial velocity of point P with respect to O prime. Now this expression is true no matter what. However, what we've done so far is that we've done this with the understanding that point P is fixed on the rigid body B. And when that's the case, the velocity of P with respect to O prime, as observed in the inertial reference frame, we've reduced that to omega, or the angular velocity of reference frame B, as observed in reference frame I, crossed with the position vector of P with respect to O prime. And this is as if we're applying the constraint that point P with respect to O prime, that the norm of this position vector is constant. And so to develop the transport equation, we're going to relax that constraint and relax that condition in which P can now move relative to point O prime. And so it can move anywhere it'd like or relative to this reference frame B. And so that means that this term is no longer valid. But it now has to consider how that point P is moving within that reference frame. So let's look more closely at that second term and develop a generalized expression that will accommodate this situation. So we have the velocity of P with respect to O prime as observed in the inertial reference frame. And that's going to be the time derivative as observed in the inertial reference frame of the position vector of R P with respect to O prime. And we define our position vector, R P with respect to O prime. Let's put some coordinates on it. We'll put Cartesian coordinates on it. So it's x, and we're going to express that in the B1 and B2 basis, plus y in the B2 direction. And this should look familiar. However, now x and y are not fixed. They can change. So when we take the time derivative of this expression, then we distribute our time derivative throughout using the chain rule, and so we get the time derivative as observed in the inertial reference frame of x multiplied times the B1 direction plus x multiplied times the time derivative as observed in the inertial reference frame of B1 plus the time derivative of y as observed in the inertial reference frame multiplied times B sub 2 plus y times the time derivative as observed in the inertial reference frame of the vector B sub 2. Now when the point P was fixed within the reference frame B, then these terms, the time derivative of x and the time derivative of y, were 0. But now none of these four terms are equal to 0, and so we have to include the time derivatives of these coordinates. Because these coordinates are scalars, the time derivative doesn't matter in which reference frame we're observing it. And so this ends up being x dot b1 from the first term, and then plus y dot b2, that's from our third term, and then we're going to add to this x times the time derivative as observed in the inertial reference frame of b1 plus y times the time derivative as observed in the inertial reference frame of b2. So let's take a look at these two sides. Here we've got x dot b1 plus y dot b2. And we call this, or this is, the velocity of p as observed in the b frame. So we've defined this as a scalar x dot b1, y dot b2, and so we can write that as the velocity of p with respect to O prime as observed in frame B. Because if you're rigidly attached, or you're fixed to frame B, and it's rotating, it's translating, it's doing whatever it's doing within the inertial reference frame, then this is exactly what you observe. You would observe the point moving at a speed in the b1 direction of x dot and a speed in the b2 direction of y dot. And then for this second set of terms, we've already solved this. This is omega b as observed in the inertial reference frame crossed with the position vector r of p with respect to O prime. Now, the big difference here from what we had before is that we no longer have the situation in which the norm of this position vector, p with respect to O prime, is constant. So this position vector now changes length regardless of where the rigid body is. And so now our expression for the velocity of p with respect to O prime as observed in the inertial reference frame, which we said is the time derivative as observed in the inertial reference frame of r p with respect to O prime, is equal to the time derivative as observed in the B frame of our position vector r of p with respect to O prime. And so that's our velocity of p with respect to O prime as observed in B, and that's the first expression for that, or the general expression for that. And then we're going to add to that omega b as observed in the inertial reference frame crossed with the position vector p with respect to O prime. And so what we have here is that we can make our observation in the body frame. We can make our observation of that time derivative in the body frame, but we want our observation to be in the inertial reference frame. And so the fudge factor here is to get from B into I, is this term omega of B as observed in I crossed with the position vector between the point that we're interested in and the point that we know that velocity. And so just to recap, we're going to make our observation and then we're going to transport it into another reference frame with this additional term. And so when finding the inertial velocity of point P in the inertial reference frame, we do the same thing we did before. So we got the velocity of point O prime with respect to O as observed in the inertial reference frame. This term stays the same, and then we add the transport equation for the next part, where it's the time derivative as observed on the frame that's moving of this position vector, p with respect to O prime, and then plus that transporting term. Now what's really cool about this transport equation is that we're going to use this time and time and time and time again. And the reason why is because this is true for any time derivative of any vector that we observe within a reference frame. So this can be a position vector like what we did here, the position of p with respect to O prime. We can do the same thing for a velocity vector to then calculate the acceleration of that point, and it's completely independent of the reference frames that are used. So I mentioned earlier that one of our main uses is to be able to change our observation from a non-inertial reference frame to an inertial reference frame. And so that's why we used B and I, and that's commonly what we do. However, The reference frames, we can go from B to A, we can go from reference frames G to Z, it doesn't matter. It's reference frame independent. But what we need to know is we need to know the angular velocity of reference frame B as observed in reference frame A. So we need to know the angular velocity of the reference frame that we're making our observations in and how that angular velocity is observed in the reference frame that we want. That's the key to this entire equation. So you'll see this idea of transporting reference frames show up through the remainder of this course, and we'll use this multiple times, and this will become one of the primary tools that you use. So begin to internalize it now, and begin to love it because it really helps us out a lot.